Alright, so now that we talked a lot about the concepts behind multilayer perceptrons, let's now get to the fun part and implement a multilayer perceptron in PyTorch. So in this first notebook, we will be looking at the XOR dataset as a warm-up exercise. And we will be implementing the multilayer perceptron as a PyTorch module. So let's get started. First we are looking at the different libraries we are going to use just for reproducibility purposes. Here are some of the version numbers. So the first real step is then loading the dataset. For that we are going to use pandas like in previous lectures. And since the file that we are going to load is already a CSV file, we don't have to provide any additional arguments to the read CSV function. So as we can see here in this dataset, we have two feature variables, x1 and x2. And there's a third column with a class label, and here we have class labels 0 and 1s, so it's a binary classification problem. And we have 750 data points in total. So next we are going to use Scikitlearn to split the dataset into a training, a validation, and a test subset. So if Scikitlearn is not yet installed on your system, you can install it via conda or just via pip with the following command by executing the following cell. Otherwise, we can continue with the next section. So personally, when I work with Scikitlearn, an old habit is to convert data frames first into NumPy arrays, just for compatibility reason and to keep the features separate from the class labels. So here, I'm creating a NumPy array that contains the two features. And here I'm creating a NumPy array, a one-dimensional array that has the class labels. Then next, I'm going to split the dataset into a training and a test subset. So here what we are going to use is the original dataset X and the label array Y. And then we are splitting it into a training array. This will contain the training features. And a test array which contains the features for the test set. So they are the same features, X1 and X2. However, the training examples are different. And we have then also the corresponding label arrays for the training set and for the test set. We're using a random state because the splitting is random. So for the random state, we then make sure every time we execute this function, we get the same splits. To be maybe more verbose, we can also say shuffle true. But by default, the shuffling parameter is already true. With stratify equals y, we make sure that the proportions of class labels, the 0s and 1s, are the same in each of the subsets. So the training and the test subset will have the same ratio of 0s and 1s in them. We will actually take a look at that in a moment. So let's execute that to split. Oops, we need to first actually run this. So let's first do this splitting where we now have the training arrays and the test set. And then in order to generate the validation set, we are going to do the same thing now, except that we are going to split the training set into a training set and a validation subset. So in this case, we use 10% of the training data for validation and 90% of the original training array, 90% of that will be used then for training. So we are just essentially splitting the training set one more time to obtain the validation set. Let's actually take a look at the dataset sizes now after splitting. So after splitting, we have the training set consisting of 573 training examples. We have 64 validation set examples, and we have 113 data points for testing. Just to make sure that the proportion of class labels is also as expected, which we essentially try to stratify via the stratified parameter here. So we are using bin count here, which counts the number of unique values in the array. So the unique values of 0s and 1s in the training label array and validation and test label arrays. And as we can see, the ratio is approximately 50-50 for all the subsets as we hoped. Now to get a better feel of how the dataset looks like, let's actually visualize the dataset. As usual, we are going to use matplotlib. And we are going to reuse the same code that we used in Unit 2 and 3. So if the code looks a bit scary, I recommend to you going back to the previous units because to save time, we're not going to go over this code again. But essentially, we are plotting here the two classes, the triangle, the orange triangle, and the blue diamond. And here you can see they are representing this toy dataset, the XOR dataset, where we have 2 features and 2 classes. And this is a problem that is very challenging for a logistic regression, because logistic regression can only do a linear decision boundary. And here the goal is to have a multilayer perceptron which can perfectly or almost perfectly classify these examples with a nonlinear decision boundary. So let's actually get to it and implement the model that we are going to use, the multilayer perceptron. So let's implement this. First, let's take a look at the init constructor, where we have a flexible number of input features and a flexible number of classes, so that we can use this exact same PyTorch multilayer perceptron class for future datasets, which may have a different number of features or class labels. So we are using the sequential API here to define the layers. We have 2 hidden layers and 1 output layer. So for the hidden layer, we accept a specific number of features that we defined up here. So we will initialize the exact number of features here when we initialize the multilayer perceptron. The first hidden layer has 25 units. So that's why we have the 25 input features here at the second hidden layer. These numbers have to match, because if this layer outputs 25 units, the second layer expects 25 input units or features. The second layer outputs 15 features, so it's a hidden layer with 15 nodes, output nodes, which then go into the output layer, and that one returns num classes, which we can set in this case to 1 or 2. So as we discussed in the lecture, 2 is more common even if we have a binary classification case. So this is here how we specify the layers. What's now missing is the forward method. So let's add the forward method here. And the forward method is pretty straightforward. We are just calling the all layers attribute here, which refers to the sequential implementation of the multilayer perceptron. And next, before we can start the training, we have to define the data loader so that we can feed data to this multilayer perceptron. So let's define the data loader. Notice that this code looks a bit scary because it's all new. We haven't really talked about data loaders yet, but we will do so actually in the next lecture. So for now, I recommend you not to worry about how this is implemented. The only thing you have to know is that we have 3 datasets: training dataset, a validation dataset, and a test set. And for those, we have 3 different data loaders. We have a data loader for the training set, for the validation set, and the test set. And yeah, we have a batch size of 32, and we shuffle the training set. We don't need to shuffle the validation or the test sets. And that's all you need to know for now. So in this notebook, we set up the dataset, loaded the dataset, and coded our multilayer perceptron in PyTorch. In the next coding notebook, we will be training our multilayer perceptron. So stay tuned for the next part.